previous lectures, we discussed about the half wave rectifier and the full wave rectifier. We discussed the bridge rectifier, center tape rectifier, calculated the various parameters of half wave and full wave rectifier, and compare the two. So today we are going to talk about the special type of diode, and under this category today we are going to discuss about the zener diode. So how we can use a zener diode, what we understand by zener diode, the construction, the working, and the diode application, the zener diode application as a voltage regulator. So this is all we are going to discuss in today's class. Okay. So what is zener diode? So zener diode is a special type of PN junction diode, and if we increase the doping of the ordinary PN junction diode, then we get a device that is the zener diode. So if we connect the zener diode in the forward bias condition, it behaves as a normal PN junction diode, but it is basically designed to work as a voltage regulator. And if you would like to use this zener diode as a voltage regulator, then it must be connected in the reverse biased condition. So you can say it is a special type of diode that permits the current not only in the forward direction as a normal PN junction diode, but also in the reverse direction if the voltage is larger than the zener voltage. If the voltage is greater than the zener voltage, the voltage which is appearing across the zener diode is greater than the zener diode voltage, then it is in a on state, and it behaves as a zener diode. So commonly available zener diodes are ranging from 1.8 volt to 200 volts, and the zener diode is used as a voltage regulator. So because zener diode is a very highly doped PN junction diode, so if increasing the doping, that means the depletion region gets reduced, and because of that reason, in the zener diode, the reverse breakdown voltage, the zener breakdown voltage occurs at an early stage as compared to the PN junction diode. So this is the characteristic curve of the zener diode. Here we can see if we are connecting the zener diode in the zener diode and the forward bias condition, then a zener diode, if zener diode is consisting of silicon type of material, then after the up to 0.7 volts, there will be no voltage is appearing across the diode, and after that 0.7 volt, your current will start flowing in the circuit. So it behaves as a normal PN junction diode in the reverse bias condition. But during the in the reverse bias, if we connect in the reverse bias condition, your diode, a zener diode, is used as a zener as a voltage regulator circuit. So you can say that if you are having a zener diode, and this is the terminal A and this is terminal B, and if the voltage, this is, let's say, the voltage VAB. So if this voltage and the zener voltage is, let's say, VZ, so if we compare these two voltages, so if your VAB is less than VZ, then diode will be in off state. So the zener is in off state, means it is open circuit. And if it is open circuit, then V0 will be equal to VAB. So whatever voltage we are applying, that will be appearing across the output. Now, if your VAB is greater than or equal to VZ, then zener diode will be in on state. This is in off state. And when it is in on state, then it will be replaced by a battery of VZ, and output will be equal to input. So output will be equal to VZ. So this is how it acts as a zener, as a voltage regulator. So up to the voltage Vz, if the voltage is appearing across the zener is less than Vz, then it will open circuit. So whatever input we are applying, the same we are going to get at the output. But if VAB, the voltage appearing across the zener diode, is greater than or equal to the designed value of the zener diode, that is Vz, then diode will be in on state, and as soon as it will be in on state, it will be replaced by a battery equal to the zener voltage, and that voltage will be appearing across the load resistance, that is Vz. So how do we start our analysis? So first of all, this is the basic circuit of the zener diode. Here we are having a resistance, the input resistance Rs, the source resistance, this is the input voltage. Here we are connecting the zener diode, and here is the load resistance is connected in parallel with the zener diode. This is the basic circuit, and the first step is remove the zener diode from the circuit and mark this terminal as A and B and calculate this VAB. We know that in parallel voltage is same, so we can say that VAB is equal to VL. Now calculating this VAB, so VAB will be equal to the voltage which is appearing across load resistance. So by using the voltage divider theorem, you can say that RL divided by R plus RL times V input. Now compare this voltage with the zener voltage. So if VAB is less than Vz, then it will remain open circuit. So output voltage will be equal to the voltage which is appearing across this terminal, that is VAB. But if your zener diode, so if VAB is less than Vz, then V0 will be equal to VAB. But if VAB is greater than or equal to Vz, then V0 will be equal to Vz. So remove the zener diode from the network, calculate V across the open circuit. If V is greater than Vz, zener diode is on, and if it is less than, then zener diode is off. This is the condition. So open circuit, the equivalent circuit will be like this, and if it is in the first case, if zener diode is on, then equivalent circuit will be like this. So zener diode will be replaced by a battery of Vz. So output voltage will be equal to Vz, because we know that in parallel voltage is same. Okay. So let us redraw the circuit. So there are the three cases could be there, that Vi is fixed, RL is fixed. Second case could be Vi is variable, RL is fixed. And third case is Vi is fixed, RL is variable. So we will be discussing the three cases one by one. So the first case, when Vi and RL both are fixed. So here we can see that this Vi is equal to the voltage which is appearing this resistance VR plus Vz. So we can say that Vi is equal to VR plus Vz, one equation. Second equation, the current which is flowing through this, that is IR, and this current is divided into two parts, that is IZ and IL. So current will be equal to IR is equal to IZ plus IL. And the one equation is V is equal to IR. So by using these three equations, we can calculate everything in the circuit. The second case could be, if we are having, the second case is when VI is variable and RL is fixed. So, if VI is variable, that means we know that VI is equal to VR plus VZ, and VZ is a fixed value because that is a designed value. So, if VI is minimum, then VR will be minimum, and if VI is maximum, if it is maximum, then this will be maximum. Also, if this value is changing and R is a fixed value, R has only a single value. So, if VR is minimum, then IR will be minimum times R, and if it is maximum, then this will be also maximum because resistance is fixed. And if IR is changing, because RL is fixed, so this and this is also fixed, VL is equal to VZ. That means this is also fixed. So if IR is maximum, that means IZ max plus IL. And if IR is minimum, then IZ minimum plus IL, because this value is fixed. Because this is fixed and this is fixed. Then the third case is when VI is fixed and RL variable. Again, draw the circuit. This is a fixed value, but this is variable. So here again, we know the two equations, that is VI is equal to VR plus VZ and IR is equal to IZ plus IL. Now, we know that VL is equal to V naught and that is equal to Vz, and that will be a fixed value for a zener diode to be in on condition. And of course, because we would like to use a zener diode as a voltage regulator, so it is mandatory to keep your zener diode in on state if you would like to use it as a zener diode, as a voltage regulator. So that means that V naught must be equal to Vz. So that is a fixed value because Vz is a fixed value. R is also have only a single value. R cannot have the various variable values. It will be a fixed value. The only two things can be variable, either Vi or RL. So here in this particular case, we are discussing that RL is variable and Vi is the fixed value. Now, because we are saying that Vi is fixed, so that means Vr is also fixed and Vz is also fixed. But IR is a fixed value, but IL is variable. So IL, if this is a fixed value, so if this is minimum, then this will be maximum. Or the second case could be if Iz is minimum. So next is if your Iz is minimum, then IL must be maximum, because this value is fixed. So that we have to keep in mind when we are discussing any, we are doing any type of the analysis. So that keeping these points in mind, we will solve the various problems. So let us start some problem. Okay. So this is the first case. Here in this case, we have Vi fixed, also RL fixed. RL is given as 1.2 kilo, whereas Vi is given as 16 volt, R is 1 kilo ohm, Vz 10 volts, and Pz max is 30 millivolts. And we have to repeat this problem by keeping RL 3 kilo. So in the first case, when we are having RL is equal to 1.2 kilo. So our first step is remove the zener diode from the circuit and calculate the voltage across this open circuit, VAB. Remove it and measure the voltage across this. This is the first case. So here, when you remove it, so calculate the voltage across this terminal, let us say VAB. So VAB is equal to RL divided by R plus RL times VI. So RL is 1.2 divided by 1 plus 1.2 into 60. So if you calculate this value, this comes out 8.73 volts. So here you can compare this voltage. Now compare this voltage with the zener voltage. So zener voltage is how much? It is given as 10 volts. Vz is 10 volts. So if you compare, we can see that VAB is less than Vz. And if VAB is less than Vz, means diode is in off state. So diode is in off state. So what will be your V naught? V naught will be equal to VAB, and that is equal to 8.73 volts. That means if the voltage is 0, that means zener no current. If it is in on, if zener is in off state, that means it will be open circuit. If it is open circuit, that means no zener current can flow. That is equal to 0. So zener current is equal to 0. That means if you are keeping this value 1.2 volts and you are having the voltage, input voltage 16 volts, then your zener diode will never come in the on state. So what is the solution? The solution is either you increase the input voltage or you change this voltage. So now coming to the next case, when we are giving RL is equal to 3 kilo ohm. So let us see the second case. If you calculate this value, here you can see that RL, again remove the zener diode and calculate the value. RL divided by R plus RL times VI. Now in this case, your RL is equal to 3 kilo ohm. So it is 3 into 16 divided by 1 plus 3 kilo ohm. So it is 412 volts. So here now VAB is greater than VZ because VZ is 10 volt. That means diode will be in on state. And if it is in on state, it will be replaced by a battery of VZ. So V0 is equal to VZ. That is 10 volt. So output is 10 volt. So if you increase this value from 1.2 kilo ohm to 3 kilo ohm, that means your diode comes in the on state. So output will be equal to 10 volts. So if your output is 10 volts, and we know that this is your voltage. So here we can calculate the current through this. So first of all, this is 16, this is 10 volt. So VR will be equal to 16 minus 10, that is 6 volt. And this is your 1 kilo ohm. That means your current will be equal to, or IR will be equal to 6 milliampere. So if IR is 6 milliampere and here this is your IL. This is 3 kilo ohm and VL is equal to 10 volts. So you can calculate IL. IL will be equal to VL, that is 10 volts divided by 3 kilo ohms, 3 into 10 to the power of minus 3. So that will be equal to 3.33 milliampere. And we know that IR is equal to IZ plus IL. So IZ will be equal to how much? 6 minus 3.33 milliampere. So how much it is? 2.67 milliampere. So that is the answer. Okay. Let us take one more problem. This is the circuit, and here you have to find out the range of RL, for which your zener diode acts as a voltage regulator. So the first step is remove the zener diode and calculate the voltage across the open circuit. So remember, whenever you need to find out the range, then first of all we have to calculate the minimum value for which your zener diode comes into the forward bias condition. Okay, the minimum value that your zener diode will be in the on state. So in that case, first of all we have to calculate the RL minimum. So remove the zener diode and calculate the voltage across the terminal A and B. So VAB is equal to RL minimum divided by R plus RL minimum times V input. So calculate this value. VAB must be equal to 12 volt to keep your zener diode in on state. So this is equal to VZ. So VZ is 12. This is equal to RL minimum divided by 1 kilo ohm plus RL minimum into V input, and V input is 50 volts. So if you solve this, it will be 12 into 10 to the power of 3 plus 12 RL minimum is equal to 50 RL minimum. So it is 12 into 10 to the power of 3 is equal to 50 minus 12 RL minimum. So 50 minus 12 is 38. So it will be equal to RL minimum is 12 divided by itna kilo. So this is the value of RL minimum. Now we have to calculate the RL maximum. So how do we calculate RL maximum? For that, this value across this is Vz, and if this is Vz, then RL and the current will be equal to, if you are saying that RL maximum, I want to calculate RL maximum and this is fixed value. So V is equal to IR, and if this is fixed, that is Vz, then RL maximum, if I want to calculate RL maximum, then IL minimum we should know. So we have to calculate this IL minimum. For IL minimum, we know that IR is equal to IZ plus IL, and because this voltage is fixed, voltage across this will be fixed, that means IR will be fixed. So if IR is fixed and we want to calculate IL minimum, then this should be maximum. One is maximum, another will be minimum, then only it will be a fixed value. So first of all, calculate the IR maximum. So IR maximum is, IR. So IR will be equal to this minus this. So VI minus VZ divided by R. So that will give IR fixed value. And that is equal to how much? 50 minus 12, that is 38 milliampere. That is your IR fixed. Once you calculate IR fixed, from this equation, you can calculate, this is PZ max and this is equal to IZ max into VZ. So from this equation, you know VZ. So we can calculate IZ maximum. So what will be your IZ maximum? IZ maximum will be equal to 32 divided by 12 milliampere. So we know IZ maximum, we know IR fixed. So here we can calculate this IL minimum. And once you calculate IL minimum by using this equation, VZ is equal to VL is equal to RL max I'll rewrite here. VL is equal to VZ is equal to RL max into IL minimum. So once you calculate IL minimum from this equation, we know this, we can calculate IL minimum. We know IL minimum, we know VZ. then Vz divided by IL minimum will give us the RL maximum. So this is how we can calculate the value of this. So this is, we have discussed the two cases. In the forthcoming lectures, we will be discussing the next third case when the VI will be the variable and RL will be fixed. And then we will calculate the few more problems on in the next video. Thank you. Jai Hind.